All right, welcome everyone. I'm truly delighted to open today's EMS webinar by welcoming Professor Klaus-Viktor Peinemann, a genuine pioneer who has dedicated most of his career to membrane science. It's a huge personal honor for me to introduce him to you today because he's a mentor I genuinely look up to, and I'm really excited for you all hearing him today. The title of his presentation is already quite telling. My Wonderful Life as a Membrane Nerd. But before we dive into his wonderful world, let me go through his impressive biography. So Klaus-Viktor Peinemann has over 40 years of experience in membrane research, spanning across academia and industry. He worked at MTR in California in the 80s and later served as a department head and senior scientist at GKSS in Germany for almost 20 years. He coordinated several European and national membrane projects. He co-founded GMT Membrane Technique in 1995, now a leading European producer of membranes for gas and vapor separation. Klaus-Viktor was president of the European Membrane Society, and since 2004, he has been an honorary professor at Leibniz University, Hanover. In 2009, he joined the newly established King Abdullah University of Science and Technology, also called as KAUST, in Saudi Arabia, where he was professor of chemical engineering. And now he's a professor emeritus at the same university and a senior advisor to GMT Membrane Technique. So, Klaus-Viktor, I'm really honored to have you here today. And as we discussed, we want to get to know you a little bit better. So we're gonna go through a couple of more informal questions. So first, what sparked your interest in membrane research? And when did that happen?
Okay. First, Georgie, let me thank very much for your very kind words. Thanks a lot. And also thank you for inviting me to this webinar, which is a great pleasure for me to talk a little bit about my membrane research and my life as nerd. Well, I think you asked how it started my interest in membranes. It was a bit strange because I started my university life in '68, a long time ago. And this was a wild time. There was Vietnam War, and I belonged then to a rather leftist group. I was a Mao Zedong fan. I changed my mind now, but then I was a Mao Zedong fan. And so it was a rather radical position. But I was interested in thermodynamics and physical chemistry. And so I applied for a master's thesis in the Institute of Physical Chemistry at the University of Kiel. But the professors there were rather conservative, and nobody accepted me because they know I'm a Mao Zedong fan. But there was one young professor, the youngest professor there, Peter Koske, and I asked him in the end. And he said, well, it's no problem for me as long as you don't start revolution at our institute, I accept you. And this was my luck because he was interested in membranes for a very specific reason. I must say, because he was interested, I will come back later to this in my talk, on recovery of uranium from seawater. And he asked me, can you make, and he was interested in the chemical speciation of uranium in seawater. Is it just an ion or is it bound to something, is it some complexes? And he thought it was quite clever. He said to me, make selective membranes where you can differentiate between just a pure ion or a complex. So this was his task for me. And I liked it. It was very challenging, something new. So this is how it started. And then my very first experience in my PhD thesis later, also with him, this experience made me to a membrane nerd. But I will explain this in the beginning of my talk.
Okay, I mean that's interesting because uranium extraction is again a very hot topic, just like it was several decades ago. So interesting. And looking back, what were the best moments of your research career? If you can
Well, yes,
some of them.
it's hard to say. It's not so easy to say. There are many very good moments, I have to say. Let me make two categories. One is, of course, when I had all of my life, I had several tasks, or I set the task myself to make specific membranes. The very first task was, this was very challenging when I made my postdoc time. They wanted to recover helium from diving gas because they spent a lot of money for helium. They had a deep diving facility and they spent, I think, for hundreds of thousands of dollars helium per year. And so they wanted to recover it, to clean it from impurities. And my goal was then, for my postdoc, make a membrane which can be used on a technical scale for helium recovery. It was a big challenge. And I knew when I can solve it, then it will be great. Then I will have a good future. And so I worked very hard. I will not go into details, but then I chose a polymer which started with my first initials, Pi, P-E-I, like my name, but it was Ultem 1000. This was a quite new polymer. And I was able, fortunately, to make an asymmetric membrane from it. And together with our engineers and technicians, we could scale it up. And within 2 years, we made a real helium recovery system for these methods. This was one of the moments. And there were other moments. I will go in my talk talking about block copolymer membranes. There was also a specific moment when we made the first self-assembled isoporous membrane. Great moment. And there was more situations like this. And the other, what was very nice for me, meeting famous membrane people. The first one was, for example, Alexander Stern. Maybe, I hope all membrane people still know him. He was a pioneer in gas separation. So I visited him. The other one was Sidney Loeb. I will show you a picture in my presentation. It was great to talk with him because he revealed some secrets to me, which I still have in my head and told to nobody. And a meeting with Richard Baker, one of the very best moments in my life was a boat tour with Richard Baker. I'll never forget it. I will show you a photo a little bit later. But there were many more situations. And start at KAUST. Also, my start in KAUST was great. I will also there show you a picture a little bit later.
Great. We are looking forward to it. So we talked about uranium, helium. So you worked in many different areas. And then you spent 20 years working as a membrane developer at a research center in Germany. And then, if I'm not mistaken, then around the age of 60, you decided to resign from that position and then you moved on. So how that came about and why did you decide to?
Yeah, so it was 59, nearly 60. Yeah, this was an unexpected decision. It came out a little bit out of the blue for me, and I expected this question because it's very unusual, because it has a very safe position, a great group, a great cooperation inside the research center where I worked. Now, I will make it short, the answer. I will not go into too many details, but for many years we had, no, let's say, the last head of the institute was Professor Paul. He was a very nice guy. Everything was nice. But then he retired, and then he was replaced by two new young heads of the institute. And there was, again, I will not go into details, but there was sometimes, probably you know something like this, there were some incompatibilities. We had really problems. They started to take some of my freedom. I need my freedom in research. And it was a lot of problems, a lot of discussions. And I already saw, I was not sure if I can solve it. But then in the end, they hired a psychologist to be present at our discussions. And when this happened, I thought, either they are crazy or I am crazy. And I couldn't answer the question because I couldn't answer it, of course, because when you are crazy, you don't think you are crazy. But this was the point. I decided, no, I stopped this. I better leave it. And this was a very good decision. It was a very risky decision, but I quit my job without having a new job at this time. But it was the right decision. So that's all. I will talk a little bit more in my presentation about this.
Okay, so it seems no regrets there. And you spend a lot of time not only in academia, but also in industry. So what is the biggest misconception that researchers in the lab have about commercial product development and vice versa? Can you talk a little bit about that? What is
Okay.
your
Well,
knowledge?
let me start with this. I'm more an academic researcher than a businessman, but of course, I have some experience with industry, especially also with our own company. And I learned with MTR, I was only a short time, but I learned a lot of there. Now, the biggest misconception is, um, well, you see in many articles and in good research articles, they end with the phrase, well, it's relatively easy to upscale these membrane. And this is in most cases a wrong statement. Uh, Also, I will not, also my own membranes, which I developed at Chaos, I wrote sometimes they can be upscaled, but most of them can be. In industry, you have to, and this I learned from Richard Baker, to keep it simple. Many solvents we use in the lab are too toxic. Industry will not do it. Many processes take that's a too long time. When I have to add a solvent extraction step, it takes 3 hours. It's too long. It's too expensive. So for industry, one has to make it as simple as possible and see all the hurdles which are there, which prevent you know. I think more than 95% of publications, what we are in academic research in membrane science, will never go into practice, which is a pity. And I always tried to my academic research to make it as practical as possible.
And what would be your recommendation for the younger generations to focus on high impact papers or focus on a more robust membrane material and scale up process that can make it to the industry? Because nowadays also in academia, translation is super important.
Yeah.
And as you said, most of the academic publications and materials that we develop in an academic setting will never make it and will never be commercialized.
Yeah.
What would you recommend?
I cannot give a very clear answer. It depends when you're a young researcher, when you already know, in case you already know what will be your future career, will it be an academic career or more an industrial one? This depends. Of course, when your aim is an academic career, probably you have to have at least a few publications in high impact journals. I think this is the situation. But in principle, my answer is it's much more important to develop some robust membrane which can be produced reproducible, which can be upscaled. This was always, at least this was always my focus. It's much better in the end for a process to have a robust membrane, even if it's not so high selective like some great membranes. But you need a robust membrane which can be produced. I think this is for me, this is much more important.
Mhm, mhm. Yeah, thank you. And now let's move from research to education. So, um, what is your opinion? What makes a professor a good lecturer? And do you have any personal teaching experience that you perhaps wanted to share with us?
Well, I can only give some personal impressions. Like I said some minutes ago, I was from the beginning of my study always interested in physics and in thermodynamics. And the lectures, when I was a student, the lectures I heard, the presentations of some professors, not all of them, some were good, but some were they didn't make contact to the audience. They gave all the equations in the correct way, but like machines, like a computer would do. I think as a professor, for me, it was always very important to look at my students, to see when some started to sleep or some started to get their mobile phone or so. And then I changed my speed. And I always try to have a more personal connection to get their interest. Or how to say it. Now, especially in thermodynamics, I liked not just give the equations for second, first, and third law of thermodynamics, but to show them how difficult it was to develop this equation for the people. Like for Ludwig Boltzmann, I like Ludwig Boltzmann. He was fighting for all his equations. He was nearly a crazy guy, but it's very interesting to show this. Or another guy, Julius Meyer, he was one of the founders of thermodynamics, and how he enthusiastic he fought to make his equations, and then he was disappointed that people did not recognize his work, and he jumped out of the window and broke his leg. Now, things like this, I like to tell stories like this, because then the students will see this is a living thing. It's well, this is my personal experience. I try to make it very, very practical, not so theoretical.
Practical and personal. All right, thank you. And I think our time is up, but maybe one final question.
Okay.
If you weren't a professor today and you didn't come across membranes at an early stage of your career, then what would you be doing today? What would your career be in? Do you have any idea?
Yeah, good question. Very likely it would be some scientific profession, some science, because now when I was 15, for example, one of my uncles, he was our uncle Dietrich, maybe no, nobody knows him, but he worked as a lab technician in Bayersdorf here in Hamburg, not far from here, and he brought me sometimes sulfur or nitric acid, quite toxic things, but I was fascinated by this. So I liked chemistry, but I also liked science. Now I see when I would not go into membrane, when I go in a new city, I usually visit a bookshop. I like bookshops. And then I'm drawn usually to the mathematical compartment. I'm not good in mathematics, but I usually go to this mathematical department and starting to read mathematics books. Maybe I would have been a mathematician or so, but I missed this. Now it's too late.
It's too late for that field, but we are glad that you remained with membranes and
Okay.
contributed to this field. Thank you very much again. I think now it's time to start your talk, My Wonderful Life as a Membrane Nerd.
Okay, great.
So the stage is yours. Thank you.
Okay, good. So let me start. Before I tell you how I started my life as membrane nerd, let me show you two other slides. Let me see here. Now I can see only part of it. Let me see. Okay. No, something is hidden on my screen, but doesn't matter. I will talk about motivations. What motivates us? Are there good and bad motivations? I think it's quite important. And let me show you this. So these is a block of motivation: help society, advance human knowledge, and so on. Do good science, follow rules, enjoy challenge. Of course, all these motivations are good. And there are other motivations, and I would not say these are bad, but they are a different category of motivation. Gain fame, public recognition, become celebrity, citations, high age factor, funding, money, power, fear, pressure, competition. Yes, of course, some are bad. Fear, pressure is always bad. And also vanity is always bad. But of course, the other one, gain fame. Most of us want to become famous, some not. But it's good public recognition is good, citation is good. We have to do it, and we need funding, we need power. But my point here is what I want to say is if these motivations, citations, gain fame, have priority above others. And I think with some colleagues, I sometimes think, oh, these have priority, then it's bad. Of course, we have these motivations, they are important, but they should not have priority. I think some colleagues I know, they are looking always for the age factor. If the age factor is 100, great. If it's 30, this is not so important like many people think. And if you just focus on this, you might do some mistakes in your scientific work. So this is an important point for me. And I asked ChatGPT, are there good and bad motivation? I was surprised. He came up with this pyramid. There was no reference. I don't know if H took it from some publication. I don't know. But this is exactly in this pyramid. You see these unhealthy extrinsic motivations, balance, extrinsic, and you should move up in this pyramid to the top. I was surprised seeing this. So, well, if somebody knows from where these come, maybe it's a publication, but there was no reference. Let me see. Oh, I want to give you several quotes. One of Richard Baker. I learned a lot from Richard Baker. And he wrote a while ago, I cannot see it in the top, but in Members Quarterly, yeah, July 2006. I hope it's still available. It's only 2 pages, but I like it very much. Doing the right thing. And I just have 2 sentences here. So he's talking there about membranes which are not stable a long time. And so the authors know the membrane are worse laid outside the lab, but to say so would destroy the beauty of their work. So they ignore this inconvenient fact. I like this sentence. And it's true. One should keep this in mind. I myself, I have to say, at the beginning of my career did this mistake. I knew the membrane was not stable, but I didn't write in the publication. One should be honest. This is the conclusion of this paper. And another nice quote is from McCutcheon in a very nice article. He says, the status quo of overselling a membrane at millimeter scale and promoting an unrealistic narrative must end. It's true. Just 2 weeks ago, I got an article as a reviewer, and for a high-ranking journal, very, very high-ranking journal. And the membrane they made, believe it or not, were 1 square millimeter, and they made all kind of measurements. I rejected it because it's not possible with a 1 square millimeter, what they claimed. But I think it was published anyway. But this is correct. Let me see what I have. I took this from the internet. There is one psychological condition called cognitive dissonance. We all know this. We all go into this trap sometimes. When you make a decision, want to buy a special car because you like it, you might block other informations. So you are, and sometimes information you have for your favorite are not really true, but you prefer these. And I added these lines here. You know, some of you know, sometimes I give public lectures about carbon capture from air. This is one of my hobbies, and I think it's nonsense. But there's always a big funding for this, and it's even increasing. And so I think what people are saying, these are comforting lies. Indeed, it's a cognitive dissonance. And when you, in my lectures, I was hoping, I knew there are a lot of people who get money, who are working in this field, carbon capture from air. But they didn't come to my lecture. I was hoping they will challenge me and say, oh, your numbers are wrong. But they avoided this because they don't want to hear this. So this is my message here is, don't go into these traps, in this cognitive dissonance. Okay, now, what made me a membrane nerd? Now is more the fun part. Well, it started indeed with uranium. I mentioned my PhD supervisor, my PhD work thesis started in 1978, a long time ago. But the lab where I was not well, nobody worked there with membranes, of course. It was a totally different topic and was quite poorly equipped. I found a little bottle with uranium salt. I found a photometer. I found one cell which I could use and an osmometer. You see here, let me see. I have to change. Let me see. This is not the original one, but a very similar one, a glass one. So this I had. So I started with this, and I made a very simple experiment because I was in one thing I was very good. I learned in my master's thesis to make extremely asymmetric cellulose acetate membrane. This was the polymer of choice then. And I could do this, very asymmetric membranes, quite selective ones. So I made the best membranes I could. I made a dilute uranium solution and put it in the osmometer. Uranyl, very dilute solution, water here. And of course, what should happen? You all know, hopefully, the osmotic law, Van 't Hoff's law for dilute solutions quite well. So what would you expect, of course, that the osmotic pressure increase on the water flows on this side. And so I did my experiments. And to my big surprise, I couldn't believe it. What happened? This did not happen. The opposite happened. The water level rise on the wrong side. So water went to the wrong side against the chemical potential. Of course, what I thought, I mixed up the solutions because it was dilute solution. Both were looking like water. I made it again, the same result. And I made it again, 3 times, enough. And then I was sure, and I was so excited because what would this mean? And I looked up in the literature. I could today maybe you can find it with ChatGPT. You find maybe things, but then no, it was impossible. I went to my supervisor. I went to the head of the institute, the boss of physical chemistry. He said it's impossible. You cannot put it in your PhD. Otherwise, if you want to publish it, you have to show why happens this. So then I was really excited. This was my start as a membrane nerd. And what I did this experiment in the afternoon. And then I built in the afternoon and in the night, a little acrylic box like this one, just a model. And a model in asymmetric membranes. I glued little barriers here with little holes here. And you see the shape like this, conic shapes. And I put little glass balls in it. Okay, a lot of glass balls, the same number of glass on each side, and I put it on the shaker. You see a horizontal shaker, not this or this, horizontal shaker. And after a while, on one side, on this side, were much more glass balls. So this fascinated me. Can it be that this happens with my asymmetric membrane, that the osmotic flows goes into the wrong direction? Then much later, I built a later equipment and put it on a, you see, let me go back. This is in a gym, in a fitness center. I put it there, my acrylic box, and let me see if I can operate it and started to shake. Can you see it? Well, and then I'll let you stop it here. But after a while, the same thing happened. On one side, all the glass balls were collected. And then they threw me out of the gym, by the way, because they didn't like it. It was because some of the glass balls were jumping out and on the floor, jumping out. They couldn't repeat it. But now think about it. For the people who are not very familiar with thermodynamics, if this really would happen with molecules, using an asymmetric method, it would violate the second law of thermodynamics. And at this, I'm a strong believer in this second law, but it's a statistical law. You never know what might happen in the future. So, and it follows me till today. Now, I don't want to waste now my valuable time, because the explanation says in the end that this didn't violate the second law. Maybe you can ask me via mail or in the question answer I tried. Its explanation is a little bit tricky. It didn't violate. I found an explanation and I could put it in my PhD thesis. But from then on, I was excited with membranes. And I said I had a very nice, he gave me a lot of freedom to do things. And he was a young pro, a lot of freedom. But the nice thing was he worked about 150 kilometers away. So I could do many things. And at this time, I thought everything is possible with membrane. For example, you see here in my young years, in my beginning of my PhD thesis, I wanted to concentrate it. It was fun, but with my good membrane, concentrate beer. So I made a lot of filtration with this little filtration cell here. And then in the end, beer looked very dark and taste was very strange. I drank a glass of it. But then after a while, my colleague made this photo. It was very strong. We never repeated this, but it was fun. Now, you asked me in the beginning, great moments in my life, and this was not too great, this moment. But this one, for example, I met this guy, so this is me, of course. This small guy here is my son. He was 3 years old then. He is now 28 or something. So it's 25 years ago. And all the membrane people should know this guy. If not, it would be bad. But this is Sidney Loeb, of course. It's Sidney Loeb. And I met him on a conference, in a party after a conference. I think it was in Israel, but I'm not quite sure, maybe in Italy. And this was a great moment. First, because I know him, he's a very famous guy, the inventor of non-solvent induced phase inversion. But especially here, we had a long conversation, and he revealed 1 or 2 secrets for me, which I still am and which I never gave away. They are still helping me to make better membranes. So this was great. And the next great guy was this one. Also this one was one of the best moments in my life. This boat tour, rather adventurous boat tour with Richard Baker. You see Richard Baker here in the front. This is Hans Weimann, and this is myself here. It was a great moment. It was a business trip with MTR. And from Richard Baker, I learned, I was only there a little bit more than 1 year, but I learned a lot of things. And Richard Baker, as probably all the membrane people should know, was a pioneer in the separation of organic vapors from air. Not only writing publications, but putting it on an industrial level. And this I learned. And I left MTR, maybe I should have stayed longer, but I left MTR in, I think in 1980, end of 1985, because my home institute here in Germany offered me a very nice position as a department. I could build a new membrane group and I couldn't resist. So I left. And at this time in 1986, we had new environmental regulation laws. So they reduced the amount of gasoline vapors, organic vapors, which could be emitted into the atmosphere very drastically to very low values. And now I knew to make the membranes. So with my group, we made the membranes. As I said in the beginning, it was a composite membranes made from polyetheramide. Pi is the abbreviation, like my name, and a very thin layer of silicone. And together with our engineering department, it was very important. We could upscale it and make it in hundreds of square meters. It was a great thing. So, and then we could build with many partners, many engineers, with companies. But of course, the membrane kind of was the heart of the whole thing. We built the very first gasoline vapor recovery unit in Europe. And it started operation in 1989. You see the people here, this was the opening day. They wanted to see it because it was the first plant. It was a great success. And at this time, they were very afraid. Of course, when you recover gasoline vapor from air, there are phases where you have explosive mixtures. You have also oxygen in the air, and they were afraid that something might explode. So they had a buffer volume here. If some fire is here, then they thought they can handle it. So later they were trust, and we didn't need this buffer volume, and it was a great thing. And it was also a very happy day for me to see my membranes working here in this thing. And then we decided to start a company because this was very successful, because many companies were asking us for the membranes, for the modules, but this was a non-profit research center where we worked, and well, we could not sell membranes. We could do something, but then we decided, Jan Wind, which is here, and myself, to start a company. And we needed a partner. We didn't have enough money to start a company to buy the machines. Our first partner was Felden, a company. They were interested in this topic. And here you see the three founders of us, Jan Wind, myself, and Klaus Ulrogge. And this is Edgar Keywords. He was the first general manager of the company from Aluminium Felden. So also this was a very happy moment, this photo on our own machine and starting the company. It started very, very small, very small. Well, sadly, I have to say, two of the guys you see here, Edgar Keywords and Klaus Ulrogge, they are not longer among us. Edgar Keywords died, I think, 2 years ago, and Klaus Ulrogge this spring. So we miss them very much, very much. I especially miss extremely Klaus Ulrogge, because he was, in the beginning, he was my boss, and then he was really my mentor, my teacher, friend, and colleague, and we started the company. And I hope we can continue the company without him like it was. So as I said, we miss him. Now, and then the whole thing went bigger. So this is a more complex thing here. It was in Bristol, at a tank farm, recovering gasoline. It's more complex here because it's the membranes. I always say membrane plant because in a way membranes is the heart, but it is a scrubber. It's a PSA unit for the fine polishing. I will not go into the details. The membrane is here, and the PSA, we have to remove the benzene because benzene, the regulation said it only 5 milligram per cubic meter or something, cannot be done with membrane. So we needed this polishing step. Okay, I will not go into this. This is not my main topic about it. Just 3 more slides about this, and then we'll come to other things. Now, Borsig membrane technology took over. They bought the share of Aluminium Felden in 2003. And this was a real success story. Together with we made the membranes and modules as GMT, and Borsig built a lot of plants, all kind of plants, like gasoline, vapor recovery, but not only this, but organic vapor, organic solvent recovery, a very big plant here, fuel gas conditioning, many of plants. I will not go through it. You can find it, many of them in this brochure, and hundreds of plants all over the world, maybe 1,000 or so. I never counted really the amount. It was a really nice success story, and it will continue. I think it will continue, might become even bigger and bigger. So I'm very happy about this. Now here you see again the three founders, myself, Jan Wind, Klaus Ulrich, when was it, 3 years ago, where we made our first 1,000,000 square meters, and always much more. I want to mention this guy. His name is Massimo Brolo. He is our master of the machines, our production manager. Without him, it would not work, because he knows every detail about, a lot of machines to make these membranes. The membrane casting machine, different coating machines, washing machines. So he's very important. One last slide of our company, this one here. Now, this is already maybe 3 years ago. Some people, there's a fluctuation. Some people left and some new people. But I'm showing this to mention this guy here. He's Thomas Besko, and he is currently our general manager of the company. And Thomas, in case you see these, thank you, Thomas, very much for making and keeping the company profitable for the last 20 years. It was a great job. Okay, I leave GMT. How can we create something new? What are innovations? I recently visited a very nice meeting, Imagine Membranes on the Azores, and this was one of the topics which we discussed there. Now, I wrote, this might surprise you. I wrote this: innovation by desperation, prohibition, adversity, competition, connecting points that were not connected before. You might think, why desperation? Why prohibition? Why adversity? Why can they promote innovation? I will show you why. I start with this example here. Desperation, yeah. First, desperation. That's my first point. Now, in 2000, I cannot read everything, but at the beginning of the 2000s, 2004 or something, I was coordinating a large European project. And one of the research topics, for me, the most important research topic, was isoporous membranes, making isoporous by membranes by self-assembly. That this is possible was known before. I mentioned one name here, Tom Russell. He is one of the pioneers in this field, and I learned from his papers. So I started just modifying his things. But my goal was, what Tom Russell was great scientifically, but it was far away from upscaling. It was not really practical. It was too complicated, too slow. But I started with his ideas, and I modified his ideas. So I take a little filter unit. I had our porous polyacrylonitrile membrane, a little layer of water, and then a layer of a dilute copolymer solution in benzene. Let the block copolymer self-assemble it at once. Benzene evaporates, and then filtrate it, and then have the layer on the pandemic. And it worked in a way, so we had, it looks like an isoporous structure. Is not, I will tell you why. Also, the cross-section doesn't look very good for me. This looks isoporous, but the dark points you see here are not really porous. They are still filled with the polyethylene oxide, which has to be etched out afterwards, which is a nasty procedure, takes too long, is not good for upscaling. And additionally, we have a lot of pinholes, and we looked at larger scales of the membranes, and I was in a bad situation because I was the coordinator, and at this time we had the project was running for a little bit more than 1 year. We had a half-time meeting, and the half-time meeting, there was a control, there was an evaluation. If you don't get the goals what you promised, it will be stopped. And this would have been terrible for me, because institution hired personnel, they would fire the personnel, and what we did so far was not much better than which was already published by other people. So I was in a state of desperation. I thought they will stop the project. Now you can do two things when you are in this state. You can, well, just surrender. and say, oh, that's life. I didn't want to do it. I really didn't want to do it. Or the other option is you think about your strengths. And one of my strengths, I have to say, is this. I said in the beginning, I know how to make asymmetric skinned membranes. All tricks. Loeb himself told me some good tricks to do this. So at this time, we worked on another project, nothing to do with this. And this is a publication of Sergei Shishatsky. So we produced membranes for hydrogen recovery from hydrogen separation of matrimide. And this was just one of our castings, a very simple one. But it made a very nice asymmetric skinned membranes. And in my state of desperation, I said, why not just replace the matrimide? But it was crazy because nobody did this. And usually the self-assembly takes a lot of time. So I was not optimistic that it might work. So what we did here, we connected points. Now it's the first time I mentioned, we connected the self-assembly with block copolymer and non-solvent-induced phase separation. So this is the process, of course. We have a casting, we have a short evaporation time, and then we precipitate the membrane in water. And this must be a competition between the normal macro phase separation, what you all know, and block copolymers. If you do it right, they make a micro phase separation, making usually ordered, self-assembled structure. But this process, at least what I thought until then, and what I was seeing in publication, takes a long time, hours. But I didn't want to wait hours. I waited only 10 seconds. I was not optimistic. But we did this, and we had a lot of luck, because this was also one of the top moments in my life. Remember, when Michael Schossek, he was at this time responsible for the electron microscope, came into my office and gave me this photo. And this is, I couldn't believe this first. You see, these are really pores now. They are not filled anymore. The pores are lined by the second block, but these are real pores. We have nice channels, we have a nice substructure of it. So it worked for some reason. It's still magic for me because it has to self-assemble very fast. And we were able to publish it in a very short time in Nature Materials, which also was a great thing, of course, for me. So, and then in the future, we try to modify this, because we did this only with one specific polymer synthesized by Peter Simon, one of the authors. And we had only a small amount of polymers, and with other polymers, it didn't work so nice. So we worked on it. And so, but when I was in middle of the work, something very unexpected happened. I opened my computer in the morning, opened the emails, and I saw this kind of email. You are not allowed to continue the work with tailor-made block copolymers. This came as a shock, but sometimes in life, this happens. And well, I didn't know what to do. I still don't know the reason why this really happened. I will not go into it, but I'm not a fighter. I can be stubborn sometimes, very much, but I'm not a real fighter. When somebody takes my freedom, I see, where can I go? What can I do? And I decided here, together with my wife Susanna and other people, just to get to a place where I get my freedom again for research. So this was a decision we did. And now, then we went to KAUST. Georgie, you mentioned it. KAUST is a new university, started in 2009. And when we went to KAUST, it was not really officially opened. It was a very early stage. And when we were very lucky that, Susanna and me were very lucky that they accepted us, because it was a complicated application process. But apparently they wanted crazy membrane developers like us. And I took this photo. This was just a few days after we arrived. It was a big firework. And I remember I said to Susanna, we looked at this firework, and I said, well, it's very nice that they welcome us and that they are happy, but this was not necessary that they make such a firework. And Susanna told me, no, it's because the official opening, the king himself was there. But I still believe they welcomed us with the firework. Let me drink a sip of water. So this was, anyway, was a great start. So this was in end of September. And then we went home for Christmas, just for a few days, back to Germany. Oh, we have it. Let me see. We went back to, let me just show and mix it up here. Yes, now I want to show why prohibition, adversity, competition. Why can this be good for innovation? Good. We went home for Christmas. And at this time at KAUST, there was one problem. The problem was KAUST was not really, the labs were not really functioning. Nobody was working there. And the procurement did not really work. They couldn't buy block copolymers from a small company in Canada. So this was our problem. We wanted to continue the work. We wanted to compete with our previous place because I knew they will also continue this. But we wanted to be the first. Now, this was competition. But the adversity was the lab was not really working. We couldn't buy the block copolymer. And believe it or not, it was Christmas, and there was a little package for me from Susanna and a package for Susanna from me. And we both managed before Christmas to order each 1 gram of block copolymer. You see here the little bottles. I got a present from Susanna, and Susanna got a present from me. So now we had 2 grams of block copolymers. This was also a great moment. Our son Victor, he was excited. He made the photo very fast. So he's not very well focused because it was a short moment under the Christmas tree. But now we had the block copolymer, and I will not tell you how we brought the solvents into, even there was no solvents, and we needed THF especially, and DMAC, I think. I'm not quite remembering it. I will not tell you how we brought the solvents, but we had then these things, and we worked very hard, I must say, but it was fun. We were the only 2 people, Susanna and myself, in the lab and making the membranes nearly, I would not say day and night, but nearly day and night. And we found out, and in the beginning, we could not reproduce it. But then we learned it just by hard work and by thinking. And we found out that the secrets are micelles. In this solution, what we have, micelles are forming, and the micelles are forming already in solution. And this was a great publication in macromolecules, I think, where the mechanism for the first time was explained. And I said, we had a lot of problems. In the beginning, it didn't work. So we had to stabilize the micelles in solution. First, we added a tiny amount of copper ions, which stabilized it. Later, we added some carbon nanotubes, and the carbon nanotubes only had the function to stabilize the self-organized micelles, which is also published in Langmuir. But later, when we found more tricks, different solvent composition, we could omit these things. And then, well, you see, we were very proud of this. This was very nice. This was the newspaper of the university, and this was the 2nd edition. The first one was just about the opening, but it was a 2nd edition, which appeared in October in 2009, I think. Yes, just 1 month after we arrived. You see, we were very fast. And the title was not, we didn't write the title, it was the journalist, Better Membranes, Adversity Drives Innovation. And it was on the front page. And the second page in this new page is this one. I like this photo in a way. You see, in the front, I'm making the membrane here, just precipitating it. Here in the back is Susanna looking at it. And when you look at the picture, you might think, oh, here's the guy who is doing the work, and he is just an observer. I like this, of course. I was the maker. But this, you might also get, if you know the truth, Susanna is not only the observer, she was kind of, I would say, the mastermind behind this, because I was happy when I made the membranes, and when I looked at it, it was a good membrane. I was not so much interested about the mechanism, but this was Susanna's work. She went into the theory and found micelles are the secrets. And so it was a very good start at KAUST. We were very happy to be in this newspaper. Yes, then we participated in a competition. There was a competition called Seed Fund. And the first prize was about $100,000, not a huge amount of money, but a nice amount of money. And you could write a proposal. And then they selected the most interesting one. for a seed fund. It was originally thought a seed fund for people who wanted to start a company. And this was our goal, to start a small company making our membranes. And we won the first prize. There were other prizes, but we won the first. I think that's probably me, Susanna, this is Matavan and Pradeep. This was our team. So and you see another picture here. You see, we are all smiling. This was a very lucky, a great time. And we had the first prize. And for the $100,000, what we did, we bought this casting machine and tried to upscale the membrane. This was only partly successful. And in the end, the machine was very useful, but we decided not to start a company. Also here, it would take too much time to go into details, but for Susanna and myself, there was a decision. We saw starting a company there was very difficult, and we should. On the other hand, we wanted to be a professor at Chaos, to teach, to have students, and we had to make a decision: the company or be a real professor at Chaos. And we decided not to start the company. There were other reasons, but I will. No, there's no time to go in this one. No, another block copolymer. I will stick a little bit for a few minutes to continue with block copolymers. And I want to mention these two guys. They were two postdocs in my group, Haisu Yu and Xiaoyang Yu. I know both in China, making, I think, quite successful work. And they selected a different block copolymer, this one here. And when they came to me and showed me, I said, no, don't use these. Molecular weight is too low, it will not give membranes. And it was true, I was right. The membranes were brittle, very difficult to make. But what they did, until to now, I don't know what points they are connected, but they were, I like them because they played around. What they did, and I don't know why they did this, they never really told it to me. They took the polymer and, like salt, they took a mixture of toluene and methanol, and like a salt, they put the powder into the polymer solution and stirring the solution. It's a bit strange, but why not? And then they took samples and made electron photographs of it. And the first sample was this one. It looks nice, they form vesicles, but this is known. It's nice, but it's known from this type of block copolymers. Good. And it was not a real great thing, but it was good, but good enough. But I would have stopped here, but they had patience. They continued. This was after, I cannot read the time here on my scale, but after many more minutes. And they continued for more time. It looked like this. I'm sure I would have stopped this. Would not be why. What should happen? It doesn't look very good. Now, after, what was it, 200 minutes or whatever, now it starts to look interesting. Now it looks interesting. Now it's it just alone, it's growing. It's just by stirring, the powder forms like this. And now I think it looks really interesting. Now, this was the end state. Now nothing happened more. You have little, very defined spheres, and these spheres, this was after, let me see, after 520 minutes or even more, 500 minutes, quite a long time. With these spheres, the spheres have a huge inner surface in these very, very ordered structures. I was excited when I saw this. And then they found, or we found, our group found, that this large surface has a very specific and very high capacity to absorb specific proteins. If you want to see details, you might look into the publication. But it was also a very creative work. This one. Briefly, I want to mention the work of Rahul. What he did also, a thing which I didn't expect. So he learned to make this standard polystyrene block polyphosphanylpyridine block copolymer membrane. This is this. And then his idea was to remove, I said before, the pores of these membranes are lined with polyphosphanylpyridine. To extract the polyphosphanylpyridine and make a pure polystyrene membrane. And when he told me this, I told him it will not work very likely because the polyphosphanylpyridine is chemically bound. And if you destroy the bounding, you will destroy the membrane. But he don't listen to me, but I gave him this freedom to continue. And he was successful because what you see here, it's a pure polystyrene membrane. As I wrote here, the first and only pure isoporous polystyrene membrane. Also, it was a great thing. I will not go into details of what he did. So, but very short, you can read it in the publication. So this is the membrane, and then he made a chemical modification of the PVP block by reaction with methyl iodine, and this modified block could be relatively easily be extracted until he had a pure polystyrene membrane. I don't know if somebody following this, but I like the idea because this membrane now has totally different properties than our original membranes. Good. And the last block copolymer I want to mention, Peinemann his work with Nexa, a pentablock copolymer. By the way, sometimes I'm making even membranes here at home because I'm a membrane nerd. But then I would like to continue some of the work with these Nexa. I wrote several mails to different companies, different persons in the company, Creighton in Houston, but they never answered. This is not very nice. But I think they stopped the production, unfortunately. If somebody knows, if not, if they didn't stop, and how can I get it? Please send me a mail. Anyway, he made. This was the original Creighton membrane, a Nexa membrane, what he received. And then Peinemann dissolved this membrane and redissolved it, but now in THF. And you see, it's a totally different structure. Totally is much more ordered on this side. And what the artist made something like this. The blue things should just the symbol for the water molecules, which have to go a little bit complicated way here. And here you can go straight ways. So Peinemann said highways for water molecules. Sometimes also the title for a publication is very good because it took a lot of people to get it. And it was a much higher selectivity now. Nexa itself, this one, has a very high water vapor nitrogen selectivity, but this was even 14 times higher. Good. Now, I leave the block copolymers. Now connecting points that were not connected before. Maybe I have a couple of 6 or 7 more slides, but not block copolymers. Now I'm sometimes using this little bit confusing figure when I want to connect points. And sometimes I bought this in a strange shop. Sometimes I use a new pair of glasses. You see, not only the glasses are different, also the shape is a bit crazy, but no, I know this. But now when I look at this, sometimes I'm dreaming a little bit, what points could we connect? And the idea of one, I think it was not originally my idea, unfortunately, but no, it's good. It was the idea of one of my PhD students. He made it. Now, this we saw already, NIPS, block copolymers, self-assembly. But what he connected is the process of NIPS, standard polymers, more or less, process of NIPS, non-solvent-induced phase separation, with polymer metal complexation. And there are very little publications, if any, on top of this. Let me just briefly explain how it works. Now, what we need for let me put on my original glasses again, then I can see it more clearly. What we need for this is a polymer, not a standard polymer, it's a polymer which can form complexes with heavy metals or with metals in general. And this one I selected. I was looking for it and I found this publication. It's an old publication. It was nothing for membranes. They wanted a high temperature polymer. When I found this, the synthesis is relatively simple. So we synthesized this polymer following their procedure. It's a polythiouracemic carbazide, PTSC. This is good. And the other one is a commercial polymer, PBI. We worked with both. And now it's the work of Francisco Villalobos. He had the idea. And I will show you what he did. This is a basic idea. Now here is the PTSC. He dissolved it in DMSO. It's a good solvent for it. And now we put it in a bath of DMSO. Now think for a few seconds. At least every chemist, every membrane guy should know what happens. It's not too interesting, isn't it? Now, of course, it dissolves, but what should it be? And is a way, you just have the glass plate. Now, of course, this was not the idea. The idea of Francisco was now he added a tiny amount, really very dilute, a very small amount of a palladium salt in the DMSO. Make the same thing. Just put these into these bars. What happens now? It's like I would call it interfacial complex formation, a little bit like interfacial polymerization. The palladium touches the film on the surface, forms a complex, and the complex is not soluble in DMSO. So it forms a very thin layer. Of course, if you wait longer, then the thickness would increase. But if you wait only maybe 5 seconds or 10 seconds, it's a very thin layer, and you can adjust the thickness by the time. And then after a short or long time, depends what you want, you put it in water bath. And now we have the normal macro phase separation. So you come up with a dense metal-rich polymer film off the top of a metal-free porous polymer support. And this is published in this journal. He made a lot of experiments. You can look it up there. And this is interesting for some applications. So now, of course, then in the end, you have to reduce, in case of palladium, the palladium salt to elementary palladium. And then we had a very thin, I think down to 10 nanometer, very thin palladium layers, more or less dense. It depends how you make the process. And this is interesting for catalytic reaction. It's interesting for hydrogen separation. And there are a lot of options there, I think. It's just the beginning of it. Very thin palladium. And I think this is my last real scientific slide. Now then Francisco chose PBI. And I will go a little bit into the detail. PBI also forms complexes with some heavy metals, also with palladium. And what we used is a triple spinneret. So in the middle is just water. Then here's our dope solution. In this channel is a solution of PBI. In this case, I'm not quite sure if it was also DMAC, but anyway, it's a solvent for PBI. And in the third channel here is the palladium salt in DMAC. Yes, in DMAC, very dilute solution. Now this has a great advantage because the last one, which I showed you, to put palladium into the precipitation bath is very difficult to upscale, very expensive because precipitation bath has some volume. Here the volume is very small, tiny volume. You just need the amount palladium which is needed for the precipitation. Now we have two processes. In the middle we have water. Now from here, now this is the hollow fiber here, right? Now here the water makes the just standard macro phase inversion. So we have a porous PBI layer. But here from the outside, the palladium solution comes and precipitates the very thin layer. I think it was a great idea and a great membrane. As I said, it's just the beginning. So some details are here. I don't know if somebody, no, this is already now 7 years ago. If somebody follows this, I think this has a lot of options. So I like this very much. And this is an example for connecting points, which are we call it CIPS, complexation-induced phase separation. Now, I'm nearly at the end, and I go back to the beginning. Uranium played a role of it. Now, this is my PhD supervisor, Peter Koske. He took me, I was very grateful for this, to Florida. And in Florida, we extracted uranium from seawater. I had a little lab there just at the beach. It was a great laboratory. And I think we extracted it by an absorber, not a membrane process, but it was a specific absorber. We extracted the largest amount of uranium, 100 gram or more, which have ever been extracted so far in this little plant. And here you see me, long time ago, and Klaus-Viktor again, who was the project head, I think, when we did these. Now with our complexing polymers, I thought maybe they can just catch some membrane from the Red Sea. So we put some of the membranes in the Red Sea water, but they didn't catch uranium. Okay, but anyway, when we started this, we made a little movie, and it was more for fun, I have to say. But I took my stand-up pedal board and I took the casting knife here, and I thought, let's make a SWIP, a seawater-induced phase inversion directly with water. So you see here, I cast the membrane with a little casting knife. Now I precipitated it in the red seawater and removed the membrane. It looks good, but it was in the end, of course, not a very great membrane because we have 3 or 4% salt in the water. So what should happen? But at this moment, it was a little movie, but I will not show the movie. I feel something touching was my foot, which was strange. So I put the membranes away and grabbed into the water, and it was a fish, nearly dead. A little bit movement there. Was it maybe some of the solvents, I don't know, were too toxic? I don't know. So we didn't repeat this experiment. And also we have a beach security which don't like these kind of experiments there. You see, but this was a fun experiment. Good, but let me show you my end slide. Which is connect points when you can, link up ideas whose connection was not previously suspected, and very important, have fun when creating new membranes, and see that you keep your freedom to make membranes, and don't let somebody say, no, you don't have to do it. Just follow your ideas if you can. Okay, thank you very much for listening.
Thank you, Klaus-Viktor. Very interesting talk. Now I know where not to go at South Beach here in Coast. Which area I should.
No, better not.
All right, so let's look at the questions. Please feel free to write your questions in the chat, and I'm gonna go through them one by one. We have a couple of questions. The first one. Haizu did a great job. Can it be extended to some other form of polymers to see the change in the morphology with time?
Oh, yes, sure. Very good question. But I cannot, but you might follow our publications, especially publications also where Haizu was involved. And you see what we did. We changed the morphology. We made the pores much smaller. Usually the spores are in the UF range or a wide nanofiltration range. And Haizu and our whole group, but with Haizu and his wife, we could make the pores much smaller to the nanofiltration range, or very interesting other thing. Yes, it can be extended in many ways, many more ways that I can think about.
Great. Second question. Similar to your isoporous membranes, which overcomes permeability selectivity trade-off, what factors should be targeted for RO membranes to increase its water permeance?
Ooh. Well, for sure, this block copolymer, this is not the right way to do this, but in general, it's difficult to answer. I have some ideas, but I'm afraid I cannot. I know what people did, and this was one idea. Usually RO membranes are made by interfacial polymerization, and this is done on top of a porous membrane. And the porous membranes, which are usually used industrially for this, they are not ideal because porosity is not very high, and we don't have an isoporous structure. Some pores are larger, some are smaller. It is not ideal. It works fine. The membranes are good. And I know people tried to use our isoporous membrane, exactly the membranes which I showed you, and make the interfacial polymerization on top of this membrane. And this is in principle a good way, because I think they found these are superior membranes. They are better. So this is in principle a way. But I think nobody followed this way for two reasons. These isoporous membranes are more difficult to upscale than I thought. There's one company, they are trying this TerraPore. I'm not really following them, and they're trying, but it's difficult. And up to now, these block coolants are very expensive, so you would not like to make RO membrane. But maybe there's another way to make isoporous membrane, a cheaper one. So this would be one way. But I will not speculate more about this.
All right, then let's move on to the next question. After having prepared so many membranes, which is the first work that comes to your mind that you would like to start from scratch from a different perspective?
It's a little bit difficult question. The first word, you mean what? How do you understand this question, Georgie?
So,
For membranes or?
so is there any membrane that you developed that if you could go back to the start and start it from scratch, you would do it differently?
Oh, I see.
Knowing what you know now with your many decades of experience.
Ah, yeah. I don't know. Maybe this is good. I have to really to think about it. Well, one of the successful membranes was the membrane for organic vapor separation. And this, I have to say, I learned from Richard Baker. So he told me the secret to make them. So there was no freedom for me to do it big. And the Blockopoli membrane, this was another one. The helium membrane, maybe. No, probably not. I cannot really say, have a clear idea about this.
Okay, fair enough. I mean, I suppose that even if it took longer, then you still learned something along the way, right? So, okay, next question. Very nice photographs of the good old times, but a bit surprised by seeing people working without safety glasses
Okay, okay.
or without t-shirts.
You're totally you're totally right. And I was hesitating to show this photo. Of course, we have one, but this was just for the photograph in this moment. Usually, you are totally right. When we're operating this machine, we have safety glasses, we have lab coats, but this one was just the photograph was there, and Pradip was there, and the photograph wanted to leave, and it was just showing stood there, but we should not have done this, but totally right. And I got some criticism because the big boss of Klaus-Viktor, he saw this and he criticized me very much. And from then on, I was very careful. We always had this safety equipment. Good
Yeah,
question.
I see. Even at the beach, you're wearing your safety glasses.
Yes, even at the beach. Yeah, at the beach, I wanted to be recognized because I had these special sunglasses. Okay, good.
Nice. Okay, next question. Where do you see the future of membrane technology with respect to green solvents and circular economy?
Oh, good. I think this is the future. It has to be the future, but it goes much more slowly than I think. Because I know there is a lot of research going on, there are a lot of green solvents. We at Kaus published some papers. Also, Susanna's group is publishing papers on green solvents with good results. But industrially, it goes very slowly. Even in our own company, I would wish that we put more effort into it. But in a company, you have to compete with many other companies. You have to be cheap. You have to be slow. But we have to do more work. That's very, very, very important. And I think this is the future. I'm very curious. I think in 10 years from now, hopefully earlier, we will not continue to use DMF and DMAC. We have to switch to green solvents and also to a circular economy. It's very important. Thanks for the question.
And by the way, what prevents that at the moment in the company? So let's say if there is an alternative green solvent with a similar price range, then would you be able to easily replace that within the company, or there are some certain restrictions that prevents you from that?
Well, there are, of course, certain restrictions. Now, to be very specifically, we are relatively small companies, and maybe in larger companies it's easier, but maybe not. So we have just a permission for very few solvents that they could go into the wastewater. I just two solvents. So we are limited to these. If we want to use new solvents, we have to get new permission, which is a restriction, but it's possible, and we would do this. And the other restriction is, now, I told you our business is running quite well. We have a lot of customers, and the machines are not running 24 hours, but they are running maybe 16 hours a day. So, and in order to use the green solvents, we have to stop the machines, we have to use it, but we have to do this. And we have one smaller pilot machine, and I hope in the future, and I'm sure we will take more effort doing this, testing this, but there are restrictions. It's not simple. It's more difficult than people in research are believing.
All right, thank you. And we have one more question. So this will be the final question, at least so far, about membrane applications. So which membrane application hasn't been properly explored yet?
Which membrane application hasn't been properly
Explored yet.
installed?
Explored, yeah.
Yeah. Okay. Let me see. One application, the first one which comes into my mind, and actually our company is quite active in it, I'm very happy, is organic solvent nanofiltration. I think this is, I see a big market there. There already is a market, and we have a number of plants, and we have some good customers doing this, but these are all up to now niche applications, but we will find many more replacing distillation. There are many opportunities. And I'm sometimes I'm wondering why it's taking so slowly. But we will see many more applications in this field. And other ones, I have some dreams. We are not working on this, but I'm interested in several things. For example, if I would start if I have a lot of funds, what I would start, I'm always, since a student, I was interested in ammonia synthesis. Ammonia synthesis is one of the big processes in the world, maybe one of the most important ones. And it's a process 100 years old. And of course, there are some improvements in the catalyst, but in principle, it's always the same. And there would be many membrane applications to do this. Just removing selectively the ammonia or with some ceramic membranes. But this is in the future. But I think people will find solution. Or the other one, I was even trying to make some experiments, is direct seawater electrolysis. You know, now to making hydrogen from water, you have first make reverse osmosis, making pure water, then you can win hydrogen. But this one, there is some research going on, but it's difficult. These are two which come spontaneously into my mind.
Great, thank you. In the meantime, more questions came up, so let's proceed with what do you think is the most promising membrane-focused research direction or membrane materials that may help to alleviate the climate emergency?
Georgie, the last one, that have what?
So the most promising membrane research directions and the most promising membrane materials to fight climate change.
To fight climate change. Okay. Good. I could give a very long answer, just few aspects of it. As I said already in the beginning, I think to fight climate change by catching carbon dioxide from air is total nonsense. Some people don't believe me, but if not, write me. And I like to give public presentation on it. So this will not work. But on the other hand, my teacher, Richard Baker, and his company, MTR, they are working on capturing carbon dioxide, but not from the air, but from power plants and from cement plants. And in KAUST is a very nice project, also catching carbon dioxide from gas-fired power plants. And now they are doing it not with membranes, but they are doing it with cryogenic procedures, which works. In the beginning, when I saw it, I thought it doesn't make sense, but I went into the number, it works. But also with membranes. Membrane or cryogenic, both are good solutions. And so this is very good. This is one topic, because especially in cement plants, this is my favorite, because cement plants, generate, I think, 7 or 8% of the total CO2 emission, and it's a high concentration, so it's very, very good. And the other one, I just said it in my previous answer, is replace distillation processes wherever it's possible with membranes. Also this one. But I have to make one remark. Many scientists, which I know in a publication, they underestimate distillation. Distillation is better than we think. Many think you cannot just make very simple calculations. They had a lot of heat recovery to look really into distillation in order to see what can be replaced. Okay, these are my spontaneous answers. CO2 capture is good from cement plants, from power plants, maybe, and replacing energy-intensive distillation processes.
All right, thank you. And then final question as of now. No, second to last. As far as I know, block polymers are often not in the equilibrium morphology after certain manufacturing techniques. Do you think this could cause problems with the application?
No, this is a very good question. Yes, you are right. They are not in equilibrium state, but so to speak, all our asymmetric membranes are not really in an equilibrium state. We produce by NIPS a non-equilibrium state. But of course, block copolymers are especially sensitive to these. Yes, for sure. For example, the membrane I showed you, the polystyrene PVP membrane, of course, one has to be very careful with certain amounts of solvent vapors. So then they would change the morphology. But we prepared them for aqueous applications. And there we made relatively long experiments, putting in water, and there we didn't see any change. But the question, you are right. One has to be careful. They might change the morphology.
All right. And then next question. I'm quite interested whether you have thought to explore the dense ion exchange membranes for concentrating or recovering rare earth elements through electrodialysis.
No. This is an interesting research topic, and I would like to learn more about it, but I have no knowledge about this which I could give you. But it's very interesting. I'm reading literature. I'm just starting to read some new publications about this, but I cannot give any comment if it's worthwhile or not. I don't know.
All right, all right. Okay, this was the last question. So
Good.
thank
I
you.
like to answer the question, but it's good because my voice is slowly fading. But it was fun to be here and to answer some questions. It's a pity that I couldn't see. Usually I said, when you ask me what should a professor do, I like to see my audience. Now there's no direct feedback, but I'm happy about the question. Thanks.
Yeah, I think the engagement was good, and you received a lot of questions. Actually, there is one more now, new questions coming in. Do you still have time? One more question?
Well, maybe one more, then I have to get
Okay.
out and get a drink.
Okay. Looking back to your journey as a membrane researcher, what is the most surprising lesson you have learned from membrane research that changed your approach as a scientist?
Oh, good question. Also not easy to answer. Probably, no, I'm sure. Probably again, what I learned in my short time at MTR with Richard Baker, because what he told me is membrane development is one thing. So this is what I like, of course, taking material, making a new kind of membrane. But I'm interested in applications. And when you want to develop a membrane from a certain process, look at the whole process. Don't just think I replace distillation. I will give you an example. When I was a young student with membranes, I gave lectures replacing cryogenic distillation for oxygen separation, because I thought membranes are much better. You have cooled down to 170 degrees, costs too much energy, but this is not true. what I learned from Richard Baker, I looked into it and then I learned cryogenic distillation for air separation is very effective. It's because it's a lot of heat recovery. You cannot beat it with membranes to produce oxygen. So you have to look at the whole process as good as you can, making a small analysis. What is the energy demand? And this changed really my approach later when I wanted to develop a membrane for a process. And very often when I was asked by some potential customers, can you make this in this membrane? I said, maybe we can make the membrane, but it's not worthwhile because it will not save energy. It will not help you. So this was very important.
Right. This was really the last question. So once again, Klaus-Viktor, thank you very much for being here with us today, sharing your professional journey and personal account on many different topics. I think it's been great and the engagement was really good. So thanks to the audience and goodbye, everyone. Enjoy your drink, Klaus.
Okay, thank
Bye-bye.
you. If
Thank
you have a
you.
question, write me a mail.